Hello, good evening to all of you.
Sir, good evening, sir.
Good evening, sir.
Good evening, sir. Namaste, sir.
Am I audible?
Yes,
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Fine, thank you. Okay, is my screen visible to you?
yes, sir.
Yes, sir.
Please answer your attendance. Aditya Kumar,
Present, sir.
Anand,
Yes, sir.
Ananta Kumar,
Yes, sir.
Arnachalam,
Yes, sir.
Hasan,
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav Prasad,
Yes, sir.
Lakshmi Narayana,
Present, sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Rahul,
Yes, sir.
Roshan Kumar,
Yes, sir.
Sabish Kumar, Satish Kumar,
After the jury, if
Titus,
Present, sir.
Valish,
Yes, sir.
Vigneshwaran,
Present, sir.
Vijayaraj,
Present, sir.
Vikash,
Present, sir.
Vivekanand,
Present, sir.
Yadav,
Present, sir.
Viraj.
Present, sir.
Thank you. Could you please mute your mic? Okay, thank you. So welcome back to this course, and we are in chapter 2. We have discussed the concepts in chapter 2. After discussing concepts, now we are discussing tutorial problems involving the concepts that we have discussed here in this chapter 2. Right. So in the last class, I discussed the solution procedure for the first 2 problems. So there are 5 problems, tutorial problems involving the concepts that we have discussed in chapter 2. You have to submit these problems. You have to solve this problem by yourself and submit it as an assignment, as already informed to you. Now, to help you to proceed with the solution, I am providing you the procedure, solution procedure. So please note down the solution procedure and solve the 5 problems that is sent to you already. Okay, and then submit this as an assignment by next week. Next week, Wednesday. Is that fine? By next Wednesday, can you submit the assignment?
Okay, sir.
Okay, sir.
Okay.
Yes, sir. We'll do it.
You can send it to my email ID. I will correct the assignment and send it to you. As I said, there are 2 assignments for this course, and the weightage is 10% of the total marks. Okay. So you solve the 5 problems and submit it, send it to my email ID. I will correct and send back to you. So now to continue with where I stopped in the last class, I discussed the procedure for solving the first 2 problems. I am proceeding to problem number 3 now. I hope all of you are able to see the tutorial sheet. Is it visible?
Yes, sir. Yes, sir. Yes, yes, sir. Yes, sir.
Fine. So I'll just read out problem 3. Considering a stoichiometric mixture of gasoline and air, determine the mole fraction of fuel, the fuel air ratio, mole fraction of H2O in the products, the temperature of products below which H2O starts to condense into liquid at 101.3 kilopascal. Gasoline is approximated as isooctane with the formula C8H18. So this problem involves stoichiometric combustion of gasoline air, and gasoline, you know, it's a multi-component fuel. So we need to make some approximation to arrive at the molecular formula with the number of carbon atom and hydrogen atom. In this problem, gasoline is approximated as isooctane with a molecular formula C8H18. You know, this is one of the hydrocarbon present in gasoline. Here we are taking only one hydrocarbon as a representative of fuel, multi-component fuel, gasoline. So this is the formula, and this gasoline undergoes combustion under stoichiometric condition. You know what a stoichiometric condition is. Gasoline undergoes combustion under stoichiometric condition with air. So it's a gasoline air stoichiometric combustion. So you have to first write the stoichiometric combustion equation for gasoline air, gasoline with the molecular formula C8H18. Based on that, you have to find the 4 parameters that are asked in the problem. The first parameter is mole fraction of the fuel. Second parameter is fuel air ratio. Third one, mole fraction of H2O in the product. And the last one is the temperature of product below which H2O start to condense into liquid. So, you know, after combustion, H2O in the product side will exist in the vapor phase, right? H2O exists in the vapor phase. So you are asked to find the temperature wherein H2O will start to condense into liquid from vapor phase to liquid phase. This is one of the important problem when you do experiments in the engine. You know that H2O present in the combustion product. H2O is one of the major species in the combustion product. Now, when you use some equipment to analyze the pollutant emission, right? So you use emission analyzer to analyze the pollutant emission. Now, if the H2O get into liquid phase and enter into the equipment, it's going to affect the instrument sensitivity, right?
Yes, sir.
Any moisture entering into the electronic equipment, you know what effect it will have. So, so you have to track and you have to find whether H2O exists in the vapor phase or liquid phase. Now, in this problem, you are asked to find what will be the temperature of the product that will make H2O to condense into liquid. Initially, it is in the vapor phase. You know, it exists at in the vapor phase at high temperature. When the temperature drops, H2O is going to condense into liquid. You are asked to find that particular temperature. Okay, that particular temperature where H2O start to condense from vapor phase to liquid phase. So as I said, first you need to write the combustion equation, gasoline air combustion equation to proceed with the solution. Gasoline molecular formula is C8H18. The first parameter is mole fraction of fuel. You know how you can find the mole fraction of fuel. Mole fraction of fuel is given by, how will you find this?
So there is a question alpha, so alpha plus alpha will be the thing, sir, actually.
No. I'm just asking you how you will get mole fraction.
Sorry. So number of mole of fuel divided by number of moles of fuel plus like air, number of mole of air.
Yeah. So general formula is Xi, mole fraction of any species, is equal to number of moles of that species divided by total moles. This total mole depends on whether the species appear in the reactant side or product side. Now you are asked to find the number of mole, you are asked to find the mole fraction of fuel. So you are writing in terms of number of moles of fuel and then total mole. So this total mole, this is total mole. Now you have to consider total moles of reactant or products.
Reactant, sir.
Total moles of reactant. So you know in the reactant you will have fuel and air. So you are writing stoichiometric combustion equation. Fuel and air, these are reactant and it forms various products. Okay, and you are asked to find the mole fraction of fuel. This is what you are finding. So that will be equal to number of moles of fuel by total mole. Total mole is the total, you have to consider both fuel and air because these two put together is reactant. These are reactants and these are products. Various species will be formed in the product. So once you write the stoichiometric combustion equation, you should be able to get this mole fraction of fuel. The second parameter asked is fuel air ratio. How will you find fuel air ratio?
So that will be basically mass of the air which will be required for burning 1 gram of fuel.
Yes. So this is stoichiometric combustion. You are asked to find fuel air ratio. Fuel air ratio here refers to mass of fuel divided by mass of air. How will you find mass of fuel by mass of air under stoichiometric condition?
So we have the chemical formula for the fuel.
You write the combustion equation in mole basis or mass basis?
Mole basis, sir.
Mole basis. You always write the equation in the mole basis. But now here you want mass. How will you get mass from mole?
Sir,
Molecular weight. Molecular mass.
Molecular
Yes.
weight of.
So can I say number of moles of fuel into molecular weight of fuel? That is what is mass, right? So you know number of moles is equal to mass by molecular mass. Molar mass or molecular weight. N is equal to small m by capital M. Capital M is molecular weight of any species. So in terms of species, you can write with the subscript I. Ni is equal to Mi by Mi. Mi is molecular weight of species I. Okay, and M is mass. So here you want mass of fuel. So you are writing number of moles of fuel multiplied by molecular weight of fuel. The denominator you are writing mass of air. Mass of air will be number of moles of air multiplied by molecular weight of air. Okay, so you know all this once you write the combustion equation. From the combustion equation, you will be able to find this. Molecular weight you can find based on the molecular formula. For each atom, there is a molecular weight, and you have to add all those to get the molecular weight of fuel. In air, you have only nitrogen and oxygen we are considering. Okay, as I already said, 79% of nitrogen and 21% of oxygen. From that, you should be able to get the molecular weight of air. Number of moles of air will come based on your stoichiometric combustion equation. Okay, from that you will get this. From this, you should be getting this mass of fuel by mass of air, which is what is asked in the problem. That is fuel air ratio. The third parameter is mole fraction of H2O. How will you find mole fraction of H2O? Same thing. Mole fraction is equal to number of moles of H2O divided by total mole. So what is the total mole you will consider here?
Product side.
Product side. So because H2O appear in the product side, so when you talk about total mole, you have to consider total moles of products. So this is total moles of products you need to consider. Under stoichiometric combustion, what are the product species you will get?
CO2, H2O, and N2.
Yeah.
Three species.
So products will be P is equal to 1. That is what is stoichiometric combustion. So the products we will be considering will be CO2, H2O, carbon bonds to CO2 under stoichiometric condition, hydrogen bonds to H2O under stoichiometric condition, then nitrogen. We are not considering oxidation of N nitrogen to NO and NO2. So we are assuming that the temperature is less, nitrogen comes out as it is. So you have these three species appearing in the product under stoichiometric condition. So you have to consider all this to get the total mole. Okay, that is how you will get mole fraction of H2O. The last parameter, temperature of product at which H2O start to condense. Can anyone tell me how you will find this temperature of product at which H2O start to condense?
So something related to partial pressure, sir? I'm not sure.
Yes. So from partial pressure, how will you get the temperature? What temperature you need to consider when you talk about condensation from vapor to liquid phase?
So I think there is a chart now, if I'm not wrong. So
Now, what is the temperature at which phase change happens? This is a basic fundamental question. What is the temperature at which phase change of any species?
Point, sir. Vapor pressure, sir.
No, I'm not asking
Boiling point.
pressure, temperature. Boiling
Point. Yes, boiling. Yes, sir. Yes, boiling point.
temperature or saturation temperature, can I say?
of
Yes,
course.
sir.
So you would have studied this temperature enthalpy diagram, right? You will have a constant pressure line, something like this. So pressure is constant here. And this temperature phase change is happening. What is this temperature called? Saturation temperature. So for each pressure, there is an associated saturation temperature. And you know, this is how it will be. This is liquid phase, this is vapor phase. Okay, here phase change start to happen at this temperature, which is called saturation temperature. Okay, so once the vapor, H2O vapor reaches this temperature, saturation temperature at this pressure, then there will be conversion from vapor phase to liquid phase. This is what is asked in the problem. Now, I need to get the saturation temperature. To get the saturation temperature, I need to know the pressure. What pressure I need to consider here?
Partial pressure, sir.
Partial pressure of H2O. Very good. What is given in the problem? What information with respect to pressure is given in the problem? 101.3. 101.3 kilopascal. What is this pressure? This is total pressure, right? 101.3 is the total pressure. Did you get what I am saying?
Yes, sir. Yes, sir.
But what you need to get for saturation temperature, you need to get pressure, partial pressure of H2O. You know, you have a gas mixture. That's just now we said that there are three species in the gas mixture in the product, CO2, H2O, and N2. Each of these species will exert some pressure. That pressure is partial pressure. So H2O will have some partial pressure, okay? CO2 will have some partial pressure and N2 will have some partial pressure. There is a total pressure, right? But what we need to consider is partial pressure of that particular species. So from this, you need to get the saturation temperature. Now, how will you get partial pressure from the total pressure?
Total pressure multiplied by mole fraction of H2O.
Mole fractions.
Yes. So partial pressure of H2O will be equal to mole fraction of H2O multiplied by total pressure. What is this law called? Dalton's law. Pi is equal to, this is a generic notation, Xi into P. P is total pressure. Pi is partial pressure of species I. Partial pressure of any species I is equal to mole fraction of that species multiplied by total pressure. This is what is Dalton's law we are applying here. Partial pressure of H2O is equal to X H2O, that is mole fraction of H2O into total pressure. This is given in the problem. How will you find the mole fraction of H2O? You already have, right? You have been asked that information also. You have this. Okay, so from this you will be able to get the saturation temperature. That is the temperature at which H2O will start to condense into liquid from vapor phase. But you have to refer something called steam table. There are standard steam tables available. From steam tables, you have to refer the steam table. Once you have this partial pressure of H2O, okay, refer the steam table. From the steam table, you will get this T saturation. That is saturation temperature at that partial pressure. This is what is asked in the problem. So at that temperature, once the product reach that temperature, H2O is going to condense into liquid phase. Clear?
Yes, sir.
Okay. So next problem, problem number 4, you are asked to get the vehicle range or mileage. Estimate the vehicle range or mileage in terms of volumetric energy content of gasoline and diesel. Take density of gasoline and diesel as 770 and 845 kilogram per meter cube, respectively. Assume equivalent engine efficiency with different fuel. Take the lower heating value of gasoline and diesel based on problem 1 solution. Take diesel as a reference fuel for comparison. Have you understood the problem? Is the problem statement given problem statement, is it clear to you? You are asked to find the vehicle range. There are 2 vehicles here. One is fuel by gasoline, which is an SI engine. Second one, fuel by diesel, which is a CI engine. You are asked to compare the mileage given by these 2 vehicles. One of the vehicle is SI engine, other one is with CI engine. You have to compare the mileage, right? And what assumption you are considering here is the efficiency, engine efficiency is same. Efficiency is same for both the engine. Engine efficiency with different fuels are same. So when you assume engine efficiency, what will in the vehicle range or mileage?
So calorific value of the fuel. Heating value. LVH.
Heating value. Anything else other than heating value?
And density also, sir.
Density. So that's why when you consider heating value and density, you will get something called volumetric energy content. What is volumetric energy content? How much of thermal energy is released by burning unit volume of the fuel. We store fuel on volume basis, right, in our vehicle. Now, based on the differences in the density of gasoline and diesel, based on the differences in the lower heating value of gasoline and diesel, the vehicle range or mileage is going to be different. You are asked to find that. Okay, we are assuming equivalent engine efficiency. So the difference in vehicle mileage is only due to difference in the volumetric energy content of the fuel. Okay, so you have to find the difference in volumetric energy content of gasoline and diesel. Consider diesel as a reference fuel. Consider diesel as a reference fuel. First, find the difference in volumetric energy content. Then consider diesel as a reference fuel. With that, you have to express the difference in mileage in terms of percentage. Okay, absolute mileage value you cannot get. You are going to get the difference in mileage in terms of percentage. Okay, basically you are finding difference in the volumetric energy content of gasoline and diesel. Take diesel as a reference fuel, express that difference in percentage. That is what is going to be the mileage difference, okay, for the 2 vehicles. Basically, if the value is negative, it means gasoline is providing less mileage. I mean, if you get the percentage with a negative value, then it means gasoline vehicle is providing less mileage than diesel vehicle. If the value is positive, it means you are getting a higher mileage with gasoline compared to diesel. Did you get what I am saying? You have to first find the volumetric energy content. So you are considering equivalent engine efficiency. You have to find the volumetric energy content. To find volumetric energy content, you need this information: density and lower heating value. This is for gasoline. Then for diesel, you also have this density and lower heating value. Find volumetric energy content based on the density and lower heating value. Find the difference in the volumetric energy content of gasoline compared to diesel, and then divide that value by diesel volumetric energy content. Right, so you will be able to get the difference in the volumetric energy content in terms of percentage. That is nothing but difference in mileage. Difference in mileage is equal to difference in the volumetric energy content of the two fuel. You may get negative value or positive value. Okay, if you get negative value, it means gasoline vehicle is providing less mileage. Clear?
Yes, sir.
The last problem number 5. Consider stoichiometric combustion of diesel air mixture at a constant temperature and pressure of 1800 Kelvin and 101.3 kilopascal respectively, using a one-step global reaction formulation for the rate constant. Estimate the time required for the complete consumption of diesel. Assume that the rate of consumption of diesel is constant and diesel is approximated as decane, C10H22. So in this problem, we are approximating diesel fuel as a single hydrocarbon, which is decane, with the molecular formula C10H22. And the problem involves stoichiometric combustion of this diesel air mixture. During this combustion event, the mean value of temperature and pressure are given 1800 Kelvin and 101.3 kilopascal. Okay, that is what is the average value of temperature and pressure during the combustion event. Using one-step global reaction formulation, we already discussed about how to calculate reaction rate for a elementary reaction as well as for a global one-step reaction. Okay, so you have to apply this global single-step reaction formulation because we are approximating this multi-component fuel diesel as one component fuel decane. So we are considering only one hydrocarbon. Now we have to apply the global single-step formulation. That is the simplest description of chemical kinetic scheme as we have discussed previously. Okay, so you have to apply this global single-step model considering diesel as decane, and with that you have to estimate the time required for the complete consumption of diesel. Okay, so you are asked to find the time that is required for the complete consumption of diesel, and you are asked to assume that the rate of consumption of diesel is constant. The rate of consumption of diesel may vary to some extent in an actual combustion. We are assuming here that the rate of consumption of diesel is constant. With that assumption, you have to find how much time is required to completely consume the diesel fuel. You are taking a finite volume of diesel fuel, right? You have to find how much time is required for the complete consumption of that finite volume of diesel fuel. This is what is asked in the problem. Okay, so you are considering diesel air stoichiometric combustion, and diesel is approximated as C10H22. Pressure and temperature are given in the problem, and you are asked to consider one-step global reaction formulation. And the data you need to find is time, small t, time required for consumption of diesel. This is the data asked in the problem. How will you find the time? Can you think of anything based on global single-step formulation? Can you think of the procedure, solution procedure to get time?
So you have told that derivative of fuel like d fuel divided by dt is equal to m fuel into QC. That is the value of HHR. So here HHR will not work here, where LHR will work. So what I mean to say, by this equation, we can get the value of Q dot R, and like what I mean to say is mass of the fuel.
So this is time. Okay, what we have discussed earlier is the rate of consumption of fuel. This is what we have discussed rate of consumption of fuel is given by minus Q dot R. This negative sign indicates that it's a consumption of fuel. Minus Q dot R. Q dot R is nothing but rate of progress of a reaction. In this case, it's a single step global reaction. Rate of progress of the reaction is given by Q dot R. And you know Q dot R can be estimated by using this equation on the right hand side. A naught exponential minus EA by R bar T. This whole thing is called rate constant K. K multiplied by fuel concentration raised to the power small a, oxygen concentration raised to the power small b. This is called law of mass action. How a chemical reaction proceeds is given by law of mass action. And what you have as a first term is the rate constant, Arrhenius rate constant K multiplied by fuel concentration raised to the power A, oxygen concentration raised to the power B. This is what we discuss when we discuss about the global single step reaction formulation. Okay, this is a model that helps you to get an estimate of rate of consumption of fuel. But what is asked in the problem is time required for consumption of diesel. Now, once you know the rate of consumption of diesel, how you can find the time of consumption, time required for consumption of diesel, right? You get the rate of consumption here. From this, you can find time. So what should you do?
So basically, mass of the fuel we have to get, and then divide by rate. So we'll get a time.
No, you need to get time. Here you are getting the rate of consumption. Rate of consumption generally chemical equation is expressed in molar basis, right? Chemical reaction. So when you say d upon dt of fuel, the unit will be mole per cc second. Mole per cc second. Mole per cc is for concentration. Anything written within the square bracket is called concentration. I already told you. Okay, concentration unit is mole per centimeter cube. So this is mole per centimeter cube. Mole per cc. And denominator you have time. So that is in second. Mole per cc second is what d upon dt fuel concentration. But what I want time in second. So what should you do? Just by looking at the unit you can tell. I want time in second. What I have from the global single step formulation is mole per cc second. What should I do to get the time in second from this?
Reverse it, sir, like 1 upon this.
1 upon this will be cc second by mole.
The concentration mole per cc divided by the rate.
Exactly, you got the point. So what you can get is you divide the concentration. Concentration is mole per cc. You divide mole per cc with mole per cc second. Divide mole per cc by mole per cc second. So then this mole cc will get cancelled. You will get time in second, which will go to numerator. So what you have to do is you have to just divide the concentration of fuel with rate of consumption of fuel. This is what I have written here. Time required for consumption of diesel is nothing but concentration of fuel divided by rate of consumption of fuel. I have introduced negative sign because time cannot be negative. D upon dt by fuel is written with a negative sign, right? That is just to indicate that it's a consumption. So this will be mole per cc. This will be mole per cc second. Once you divide this two, you are going to get time in second. This is what you want. Okay, so you have to get the concentration of fuel and you need to get the d upon dt of fuel. So it means you have to first use this equation, get mole per cc second, also find concentration of fuel in mole per cc. From this two, you will be able to get the time required for consumption of diesel. Okay, so now here, one of the important thing you need to look at is the units of the parameters. So pay attention to units of all the parameter. You have to pay careful attention here because I have also circulated a table to you. The table will be used to solve the problem. In the table, if you look at the table I have given to you, what is given in this table is global reaction rate constants. So some constants, whatever we have discussed now, those constants are given in this table for important hydrocarbon. The left hand side you could see several hydrocarbons, CH4, C2, H6, C3, H8 and so on. For this different hydrocarbon, the values provided to you are one is A0, the other one, second one is EA, activation energy. This is free exponential factor. Third one is small a, then B. I already told you that you can get these information A0, EA, small a and b based on experiments done in shock tube or flow reactors. So this research group has done experiments in shock tubes and flow reactors, and they have arrived at these values for the hydrocarbon listed out in the left side. Okay, left side of the table. Only thing you have to be careful when you use this data is you could see that the data is given in a particular unit. For example, activation energy is given in kilocalorie per mole. Okay, which is not a standard SI unit. A0 is given in mole per cc centimeter cube raised to the power 1 minus a minus b by second, which is again not a standard SI unit. So these are the units they have used based on the experiments they have done. So in order to solve the problem using this information from the table, you have to pay attention to the units, because you need to see that the units that you are substituting are consistent. For example, what is the unit for R bar? Standard unit. R bar is universal gas constant. Which is
Joule per mole per Kelvin, if I'm not wrong.
So this is, if I write the value, it is 8.314. You can write joule per mole or kilojoule per kilomole.
Okay.
Kilojoule, kilomole, Kelvin. 8.314 kilojoule, kilomole, Kelvin, right? What is the unit for temperature? Temperature is Kelvin. So once you multiply R bar and T, what will be the final unit? Kelvin will get cancelled. You will get kilojoule per kilomole, right? Now, in the table, what is the unit given for EA? Unit
kilocalorie.
Yes, kilocalorie per mole. Okay. So here I am substituting, suppose in kilocalorie per mole, this is what I will get from the table. Okay, then the units are not balanced. The numerator you have kilocalorie per mole, the denominator you have kilojoule per kilomole. So what should you do? You convert this into kilojoule per kilomole. Then the units are consistent. You cannot use different units in the numerator and denominator. Okay, you will end up in getting a wrong value. So the values given in the table are this. You need to convert this to this so that the units are consistent. So at the end of the day, this numerator and denominator both are kilojoule per kilomole. This will cancel out. Now come back to this A0. A0 is given in mole. Looking back at the table, you could see at the footnote, unit of A0 is mole per cc, that is centimeter cube, raised to the power 1 minus a minus b divided by second. This is a unit they have given. So mole per cc raised to the power 1 minus a minus b divided by second. Okay. So it means you have to get this fuel concentration in mole per cc so that you will get mole per cc A. Oxygen concentration in mole per cc so that you get mole per cc B. So that is what you have for A0. So this A and B will cancel out. Finally, you will get this in QR in mole per cc second. This is what you have written here also for d upon dt of fuel concentration. So that is equal to minus Q dot R. So it means Q dot R unit is mole per cc second because of the unit for A0. A0 is mole per cc raised to the power 1 minus a minus b by second. Okay, so you have to get this fuel and oxygen concentration in this unit, mole per cc unit. Fuel concentration and oxygen concentration, how will you find? How will you find the concentration?
PV is equal to nRT, sir.
Equation of state you have to apply. PV equal to N R bar T. For species I, let us say it is PIV Ni R bar T. So it means Pi is equal to Ni by V R bar T. Ni by V is nothing but concentration of the species. Concentration is indicated with a square bracket. Okay, this is Pi and Pi. This is Ci R bar T. Pi, what I have to find is concentration. So this is Pi by R bar T. Pi can be expressed in terms of total pressure. So what will be the equation? XIP divided by R bar T, right? So this is the equation you are going to use to get concentration of any species. Okay, this is a standard notation you are writing within bracket, and this is obtained from the equation of state and Dalton's law. Concentration of any species is Xi P R bar T. Now, if you look at carefully, if you use standard SI unit, what will be the unit for pressure? Mole fraction has no unit. So this doesn't has any unit. Pressure, say you are substituting in kilopascal, temperature in Kelvin, R bar universal gas constant. Again, it will be kilojoule per kilomole Kelvin. So this Kelvin will get cancelled. You are getting kilojoule per kilomole for R bar. I mean, in the denominator term, you get finally kilojoule per kilomole unit. Numerator term, Xi has no unit. P pressure has kilopascal unit. Okay, so with this kilopascal and kilojoule per kilomole, if you simplify, concentration you will get in standard SI unit, that is kilomole per meter cube. Okay, based on the units you substitute, standard unit you substitute for the parameters on the right hand side, you will get concentration in kilomole per meter cube. But in the rate equation, you have to get mole per centimeter cube. Okay, so what you get based on standard SI unit is kilomole per meter cube. You have to convert this into mole per centimeter cube. This is what you do before you substitute fuel concentration in this rate equation, Q dot R equation. Similarly, you do it for oxygen. Clear?
Yes, sir.
So that is how you have to pay attention to the unit. Okay, otherwise you will end up in getting a wrong value. So there are several parameters with different units. So pay attention to the unit and see that they are consistent according to the given information. So with this, you should be able to solve and get the value of the time that is required for the consumption of diesel. You are going to get it from the fuel concentration and rate of consumption of fuel, that is d upon dt of fuel. Okay. So that is how you are going to proceed and get the solution for problem 5. So with this, chapter 2 is over. We are now moving to chapter 3.
Professor, one question I want to ask.
Yeah.
Can I ask, sir, if you allow, sir? Sir, regarding that, the stoichiometric equation that we have learned through your notes, like C alpha plus H beta plus alpha plus beta by 4, O2 plus 3.76 N2. This is the fuel plus air ka, what I mean to say is equation.
Yes.
Now, while calculating the mole of air, sir, what we have discussed is like alpha plus beta 4 into 3 into 4.76. Right, sir?
Yes.
Sir, I just want to ask one thing is O2 plus 3.76 N2 is basically the chemical composition of air, right, sir?
Yes.
So why we are like 1 mole of oxygen will contain 3.76 mole of nitrogen? Why we are again multiplying it by 4.76? I'm sorry, is a stupid question, but still I was thinking.
So this is the equation you are talking.
Right.
I'll just complete it.
N2.
This is stoichiometric combustion equation
Right.
for any hydrocarbon. Okay, so what is your question here?
So my question over here is O2 plus 3.76 N2 is the complete equation for the air, right, sir?
Yeah, this is fuel.
Chemical representation of air.
Yes, this is air.
Right, sir. So if I get alpha plus beta by 4, alpha plus beta by 4, that is the mole of air present in this system, in this equation. Why I'm multiplying it with like 4.76? I could get it because 1 mole of oxygen will require 3 mole of 3.76 mole of nitrogen, and hence we are multiplying it. But is that right, sir? What I mean to say is,
why your question is why I am multiplying this with 1.3.1 plus 3.76, which is 4.76. So what you are doing is alpha plus beta by 4 multiplied by 4.76. Every time you are using this to indicate the air mole. Right. Your question is why I have to multiply it by 4.76. I can done with alpha plus beta by 4 alone.
Exactly, precisely, sir. That is the question.
Not this. Right? You can do that when you combust with oxygen.
Okay.
When you have a hydrocarbon oxygen combustion, it will be only alpha plus beta by 4. But what you are doing is it's hydrocarbon air combustion. In hydrocarbon air, stoichiometric equation is written for 1 mole of oxygen multiplied by so many moles. Okay, but each mole of oxygen is accompanied with 3.76 mole of nitrogen in air. So in air, you know how you get this number 3.76. That is because 79% nitrogen, only 21% oxygen. Since you use air for combustion, you have to multiply it by 4.76 because each mole of oxygen is accompanied with 3.76 moles of nitrogen. So when you talk about air mole, it is 1 mole of oxygen plus 3.76 mole of nitrogen. Total is 4.76 moles. So when you talk about air moles, you have to consider 4.76 multiplied by alpha plus beta by 4. Alpha plus beta by 4 is based on the fuel. But for air, you always have 1 plus 3.76. If it is oxygen, it's only 1.
Thank you, sir. Thank you so much. I got it completely.
So this is air combustion, hydrocarbon air combustion. So always this coefficient is multiplied with 4.76 because only for oxygen, it is alpha plus beta by 4. But for nitrogen, again, you have 3.76 multiplied by alpha plus beta by 4. You understand?
I got it, sir. Thank you. Thank you so much.
Fine.
Thank you so much.
Are there any other questions? Okay, so now let us move on to chapter number 3. So chapter number 3 is about actual combustion event in SI and CI engine. These are the contents we are going to discuss in this chapter number 3. First, I will start with the SI engine combustion, and then I will discuss about CI engine combustion. Both for SI and CI engine combustion, the sequence of contents that we are going to discuss will be in the same order, whatever I have provided here. It will be the same order will be followed, right? So these are the contents we are going to discuss both for SI engine combustion and CI engine combustion. I will start with the spark ignited engine combustion initially, and then I will move on to compression ignited engine combustion. Okay. So I will first start with an overview of combustion process in SI engine. Okay, how the combustion event is happening. I will provide an overview of the combustion event, and then I will discuss about the stages of SI engine combustion. Here we are characterizing the combustion event through different stages. Okay, so what do you mean by characterizing the combustion event? So we are going to see that the SI engine combustion happens in different stages. So this is what I mean by characterizing the combustion event. Why do we have to do that? Why do we have to characterize the combustion event? The idea behind this is once you characterize the combustion event in terms of different stages, you can bring out the various factors that affect each of these stages. So when I say factors, these factors are variables which can be engine design based variable or engine operating condition based variable. Okay, so these variables will help you to have a control over different stages of combustion. So what we want here is a controlled or a progressive spark ignited engine combustion. You want to have a control over the combustion event through different parameters, engine design parameters or operating condition based parameters. You need to first have an understanding about these parameters effect, right? Once you know that, you can utilize this parameter to control the combustion. The question is, why do we have to control combustion? Why do we have to control combustion event?
To avoid knocking, sir, because
to avoid knocking, to avoid any unwanted phenomena like knocking. Anything else?
To get a better efficiency and reduce emission.
Better efficiency and reduce emissions. Exactly. So whenever you do any analysis on engine or whenever you do engine development, engine R&D focus is only two target. One is performance improvement. For end user, he won't worry about user of a vehicle, right? We don't worry about the pollutant that are emitted from the vehicle, right? But for OEM, that is a major consideration because otherwise you cannot sell the vehicle legally in the market. You have to comply with the current emission norm. So you have to ensure that the concentration of the pollutant, regulated pollutant, fall below the legal norm. So it is one of the major consideration when you design or develop a new engine, and before you launch it, you have to ensure that the pollutant concentration is below the legal limits. The second consideration is performance improvement. As an end user of the vehicle, I won't worry about how much pollutant, generally we won't worry about how much pollutant is emitted from the tailpipe because we are not keeping track of that. What we want? Better mileage. Okay, as a user of a vehicle, the first thing we will check is apart from comfort, the major thing we always check is mileage from an economical consideration. We want a vehicle that provides better mileage. This is what I mean by performance improvement. So we have two target: performance improvement in terms of higher mileage with a given power or torque output. Second one, we want to reduce pollutant below the legal norm. Otherwise, you cannot sell the vehicle in the market. So these two, performance improvement or pollutant reduction, primarily dependent on how the combustion event is happening in the engine. Combustion process is central to affecting engine performance as well as pollutant concentration. The way the combustion event is executed in an engine is going to design whether the engine will perform well or not, whether the pollutant concentration is within the legal limit or not. Combustion is what is affecting both. That's why we need to have an understanding about this combustion event, and we need to control the combustion event using engine design or operating variable so that you have better performance with minimal pollutant emission. So we will first characterize the combustion in terms of different stages, and then we will bring out the various factors that control or influence the different stages of combustion. Okay. Then we are going to discuss about abnormal or knocking combustion, which is an unwanted phenomena, which is going to have a detrimental effect. We briefly discussed this in chapter 1 when we discussed about the role of fuel in avoiding knocking combustion. We talked about antenna quality and all. So here we will first discuss about the basic physics involved in creating knocking, how the knocking event is produced in an engine, SI engine. We will discuss about that. Okay, the basic phenomena we will discuss and understand how it is happening. Once you have an understanding about the phenomena, we will devise suitable methodology. So we will see what kind of methodology or approach we can follow to avoid this unwanted knocking combustion, because this, the worst case scenario is it's going to damage the engine, right? And the minimal effect, it will create some vibration or noise, discomfort to the user, end user of the vehicle. Okay, that is what the knocking will do. Either it will create a discomfort to a minimal effect, and the maximal detrimental effect is it's going to damage the engine. So we need to understand how this phenomena is happening in an engine, what is the mechanism involved, and then we will discuss about how we can control or mitigate this knocking phenomena from SI engine. Finally, we are going to discuss about the combustion chambers for SI engine. We are going to discuss what kind of combustion chamber design are available. This is important because this is a chamber. The combustion chamber is a location where the combustion phenomena is taking place. We are going to see that based on the design of the combustion chamber, there is a considerable influence on the event, combustion event. How you design the combustion chamber is going to affect the combustion event that happens both in SI engine and CI engine. So we are going to look at what type of chamber designs we have and how it influences the combustion phenomena. This is what we are going to discuss in the last part of the chapter. So I will follow this sequence of content. First, I will start with SI engine. Then I will discuss about CA engine. I will follow the same sequence of content. Okay. So this is what we are going to discuss in this chapter 3. So with this overview, I stop here. If you have any questions, I will take it up. I will continue this in the next class. If there are any questions, you can ask me now.
Sir, one question regarding this octane number measurement procedure, sir.
Yes.
What we discussed in the previous class. So for cetane number, we have a criteria that we'll be varying the compression ratio until we have certain degree of ignition delay. For objective number of 13, is there any such thing for NOx also, for the SI engine?
SI engine, what I said is we are going to vary the compression ratio until the engine knocks. So we are going to measure the knock. Basically, the CFR engine, we allow it to knock when you do the measurement of octane number or cetane number. In SI engine, CFR, SI version of a CFR engine, we are going to vary the compression ratio until the engine knocks. Okay, and how do you characterize knock? By using a knock meter, you can measure the knock intensity. Until the engine knocks with the standard knock intensity, you are going to vary the compression ratio. That is a reference point. Like in CA engine, you set 13-degree ignition delay time as a reference. In SI engine, the reference is knock with a standard intensity.
Okay, sir. Thank you.
Fine. Any other questions? Okay, I'll stop here. I will see you on Monday. Thank you.
Thank you so much, sir.
Yeah,
Yeah.
thanks a lot, sir. Thank you.
Thank you. Bye.
Thank you, sir.
Yeah, thank you.